After this point, we have discussed occupation number basis. And how it allows more general set of operators. In this lecture, we will so in particular there are operators which do not preserve the number of particles for example something like this. And these operators are only possible in the occupation number basis. These okay. So this is a very convenient, but later in the future lectures we will see that firstly when we put special relativity, plus quantum dynamics, then it implies that particle number is not conserved. In the language of Steven Weinberg, there is nothing like relativistic quantum mechanics. So quantum mechanics is a formalism where particle number is conserved and hence there is nothing like a consistent relativistic quantum mechanics. So we will see that in future lecture. In lecture 3 and 4 we will see these aspects, that what do I mean by that, what is not relativistic quantum mechanics. But bottom line is that special relativity and quantum dynamics implies that we need to use occupation number basis. This is not a choice, this is a compulsion. Now, in the absence of special relativity, so in non-relativistic systems, we can use the formalism of quantum mechanics but if we have multiple indistinguishable particles, then it is better to use occupation number basis because statistics is inbuilt into it. Okay, so that's basically the context, the bigger context for using occupation number basis. And now we will try to see that how in this occupation number basis, what do we mean by quantum fields and how quantum field is useful in this case. Okay. So in this case, in case of so we have seen that from the single particle state we have got the wave function. Then we construct this following object. Oh, I'm sorry, ij was the state index actually. So technically this is not necessarily a sum, it can be an integral also. So we sometimes denote in this way, that if it's a discrete then it's summation, if it's continuous then it's integral. But it's basically an object we are constructing out of all the states of a quantum system by assigning it with a creation or an annihilation. This is annihilation, this is the creation operators. Okay, and this object that we have defined at this point ad hocly is called quantum fields. So in the later part of the lecture we will see that we will not start from a quantum mechanical system and then define quantum fields. We'll actually do an opposite, we'll do it in a different way. We'll start from classical fields and then we will try to introduce, quantize that to get the quantum fields. But this is one way also to think about quantum fields, that given a system of multiple quantum particles, I can define these operators, and they are called quantum fields. So you can also verify one important thing. Okay, so this is one very important property. Note that this summation, one important thing is that this summation or integration, it has nothing to do with space time. This is summation over states. Okay, so then given that, and given the creation and the commutation relation between AI and AJ dagger, and then the property, orthogonality property of the this wave function. So these are the wave functions of the states. This follows. So fields obey canonical quantization, but Kronecker delta is replaced by Dirac delta. Okay, so this is one thing to remember. And this step is often known as second quantization. But this phrase is misleading because we never quantize a system second times. We never do that. In this case, this commutation relation just follows from the quantization that we have done once for the free part, for the individual quantum systems. Or in the later half of the course, we will see that we only start from a classical field and we quantize it. Okay, we never quantize a system second time. Okay, so we write it. Okay, so this is one very important thing to remember. Now you must be wondering that what is the usefulness of that. So let's start from a multiparticle state. With the following Hamiltonian. So this is the full Hamiltonian, and when it acts on the multiparticle in this product wave function, it gives me the energy of the state. Okay, then the important thing is that once this is in the multi-particle language, and the claim is that this thing is same as, actually you can construct the following object, you can check it. So this was in the language of multi-particle Hilbert spaces in the product representation, and this is the same Hamiltonian. In the occupation number basis. Okay, so the important thing is that if I just start from this expression, then I automatically get the A's and A daggers from the definition, and it automatically knows about the occupation number basis. So that can be a starting point or alternative starting point. Is to consider this equation as the first beginning equation. And quantize the fields using this canonical commutation relation. Okay, so let me try to rephrase it once again. What we tried to understand here, that what I try to say is that firstly we define these quantum fields. So in our way, when we started from multi-particle Hilbert space, we started from this quantum multi-particle Hilbert spaces, and we defined the quantum fields in terms of the wave function and this ad hocly defined A and A dagger operator. But important thing is that we found that they obey this canonical commutation relation. Okay, and then what we have claimed here, this part we did not show, but this you can check very easily, because if you start from this Hamiltonian, so this is the Hamiltonian in the language of, in the quantum mechanical language, in the language of multi-particle quantum mechanics, in the product basis, I can define it the same Hamiltonian, but now in terms of phi's and phi daggers, and this Hamiltonian is the natural Hamiltonian in the occupation number basis. So this is the product basis. And this is the occupation number basis. Okay, and important thing is that this Hamiltonian, since it's in the occupation number basis, it automatically knows about statistics. Okay, but In the last, what I said is a completely alternative starting point, and this starting point has nothing to do with what we have discussed up to this point. In this starting point, you forget about everything that we have discussed by now. You just think that this is some classical Hamiltonian in terms of some classical fields phi's and phi daggers that are given. And in that process, we start from this Hamiltonian and we just quantize it using this canonical quantization relation. Also with this. So these are canonical quantization relations. And the statement is that if you start from that Hamiltonian with in terms of the fields, and if you canonically quantize the fields, then you automatically get this multi-particle Hilbert space and all this thing. Okay, so that's the important thing, and in the lecture, in the main part of the course, we will follow this perspective. I mean, you people will get enough practice that how you start from a classical field and how to quantize and all this thing. So the main part of the course will be about this second approach or the alternative approach. But what I wanted to convey is that this second approach or the alternative approach is a very natural language to the second approach or the alternative approach is a very natural language to kind of quantize to know about quantum indistinguishable quantum particles. Okay, so that's basically the motivation to study quantum fields. That it is a formalism with inbuilt statistics, inbuilt information of statistics, and allows us to change the number of particles. And changing the number of particles is absolutely necessary. This is necessary in presence of relativity. Okay, so we conclude here, and in the next lectures we will see that how special relativity and quantum mechanics creates a problem. So that will basically justify this statement.